Good afternoon, everyone. Welcome to the November Colloquium. I'm Dario Poletti from SUTD. And today it's our great pleasure to have Giuseppe Carleo. He is currently at EPFL. He joined in September. Before he was at the Flatiron Institute and before that he was at ETH and an Institute of TIC, where he was working on Quantum Monte Carlo, if I understand well, and so he did in his PhD at CISA in Trieste. And then life took a very interesting turn for him when he came out with this idea and this seminal paper in 2017 on using neural networks to do quantum many-body physics. And that skyrocketed him in the stratosphere of computational physics now. If you check out his Google Scholar page, you will see a beautiful exponential growth of citations, and he has done a very nice works in this direction, but also in using neural networks for tomography. So, and there is a nice review by him and a few other authors like Sirac and so on machine learning and many-body physics and quantum physics. So I think we can learn a lot from him today, and it's our pleasure to have him. And the floor is yours, Giuseppe. Thank you.
Thank you, Dario, for the nice introduction, and of course, thank you for inviting me here today. It would be vastly better if I could have the chance of being actually in Singapore at this point, but unfortunately, given the times, that's what we have. But anyways, I think that we can still have a nice discussion, and of course, what I would like to do today is to give you an overview of what we've been doing, and also others have been doing in the field of using and actually also devising new machine learning techniques to study problems in quantum science, in quantum many-body science. But I mean, since this is a colloquium, I also wanted to give you at the beginning maybe a little broader overview of what I would call the machine learning phenomenon in physics. As Dario was saying, there's been some interest not only in quantum physics, but also in other fields of physics. So, I mean, if you do a small exercise and you go on the archive and you look for papers in the past 12 months that have these keywords, physics and machine learning, so essentially you will see that, and this is a much better, example of exponential growth. You will see that only in the past year you have something like 3,000 papers. And there's really like a true phenomenon, which I mean, to some extent it's also a social phenomenon because people like to do what other people are doing. So there's also this component. But this is also, apart from this, if you want a social phenomenon, there's also a natural scientific phenomenon going on. And indeed, the question is why all of this is happening now. So is this coincidental? I mean, why is this happening all at the same time, or at least in the past few years? We've witnessed this increased interest in the use of machine learning for science. I mean, the question to this, the answer to this question is that essentially, apart from some hype, which is certainly there and we cannot hide, there is, however, some strong and some rather fundamental interest in deep learning, especially, which is one of the flavors of machine learning, because we are living what we can call the golden age of deep learning. Okay? So the golden age of deep learning is essentially the decade that that ended with 2020, likely for many reasons, but the 2020 was not the great year. But in any case, this decade has been marked quite strongly by the rise of machine learning as a computational technique applied to industrial problems that has allowed people to really solve some tasks that it was not possible to solve before. So apart from some hype, which is there's actually been actual strong and really tangible results that have been obtained with machine learning. So for example, if you think about the problem of recognizing images or speech. So essentially, for example, speech recognition, when I talk, and then a computer essentially transcribes what I'm saying in as a form of text. Around 2014, powered by deep learning, essentially these kind of techniques are now able to achieve human level performances in image classification or in speech recognition, starting from 2014, thanks to deep learning. So other kinds of successes, for example, in more complicated tasks like language translation. So in this case, and again, thanks to deep learning, starting from 2016, it has been estimated that tools like, for example, Google Translate that are based on deep learning can achieve on isolated sentences the same level of human translator level. And I'm pretty sure that all of you have noticed that the improvements of this technology has been quite substantial in the past few years. I mean, if you try to translate something with Google Translate, I don't know, maybe 6 years ago, the quality was really terrible, but these days it's really much better, and this is powered by deep learning techniques. And I mean, something that personally has somehow strongly motivated me to move into this field was what was achieved actually in 2016 by Google DeepMind. So now DeepMind was now part of Google, when essentially they showed that for the first time they could devise a deep learning architecture that was able to beat the world champion of Go. It was really a premiere in the sense that devising some automatic technique to play Go was the dream of the field of artificial intelligence that was not possible before the advent of deep learning. So it's clear that deep learning has really seen a tremendous growth in terms of performance and applications in the past decade. And so this is mainly the reason why also in science we are now seeing these applications. But I mean, before going there, I mean, since again this is a general seminar, I wanted also to give you slight introduction to clarify some terms. So essentially, what aspects of machine learning I will be interested in, and to some extent also what machine learning is. I mean, at least for what concerns my perspective today. So machine learning, and again, for the purposes of this talk, even though this is a good approximation in general, is and can be thought of as a set of very powerful numerical techniques that allow us to approximate some unknown, typically high-dimensional functions. Okay? So this is really, if you want, the mathematical task that I'm going to study, if you want, that I'm going to talk about today. So approximating a possibly complex and unknown high-dimensional function. And a very important remark that has to be done, clarified, is that typically AI and machine learning are not at all synonyms, in the sense that AI is a much broader and much more ambitious, if you want, endeavor, where you really want to have some independent and intelligence capable of thinking and judging also and interacting with the environment. Machine learning instead, it's a much less ambitious to some extent, but that's essentially the state of the art of what we have until now. Endeavor where we don't have the aim of having an independent sentient entity, but we have just we are solving a problem where we want to approximate high-dimensional functions. And as I will show you, this is important to automatize, for example, a lot of tasks. For example, the high-dimensional functions that I have in mind that are approximated by these deep learning techniques are, for example, those high-dimensional functions that correspond to the task, one of those tasks that I was highlighting before. So, for example, if you look at the problem of translating from, let's say, from English to Japanese, then what you're really after is finding a good approximation of a high-dimensional function that takes as an input this string of text in English and returns as an output the string of text translated in the other language. Okay, so this is a very complicated, if you want. It's an approximation of the brain of a translator, if you want, but it's in principle a high-dimensional function that is very well defined. Okay, but there are more complicated high-dimensional functions, even more complicated. For example, those that would allow you to perform autonomous driving. So in an essence, I have all the inputs of what's going on around my car. I have the radars that tell me where the obstacles are, and then this function as a function takes these inputs, so these variables, what it's seeing around it, and then decides what to do. So what the car should do to go from point A to point B, hopefully without crashing into any people. Okay. And I mean, then there are other examples of function, but essentially all the problems that I was highlighting before can be rephrased in terms of finding approximations of high-dimensional functions. Now, so how do we approximate these functions? Well, the first ingredient that you need is the machine. So we are doing machine learning. So the first ingredient that we need is the machine. And typically, especially in deep learning, the machine in question is a deep network. So what is a deep network? A deep network is my high-dimensional function. And essentially, it's a function f of some input x that in general is high-dimensional, for example, a string of text. And what this neural network does is that it takes this vector, it transforms it with a linear transformation W. So this is just a vector, a matrix applied onto a vector. W is a matrix of weights. Then you apply a nonlinear transformation on this output, so on this vector component-wise, and you get another vector. And then you repeat this operation. So essentially, you apply another linearity, another nonlinearity, another nonlinear function component-wise, until you reach the end of this network. So you have a lot of layers. So that's why this thing is called deep, because you typically have a lot of layers. And this is loosely, but very loosely inspired by the physiology of the brain, in the sense that we believe, again, with some strong assumptions and approximations, that this is how neurons work. So a neuron essentially takes a lot of input electric signal from another layer of neurons that are below them. If the incoming electric signal, which is weighted by this matrix of connectivity, essentially, is larger than some threshold. So for example, you can think that this G is nothing but like a threshold function that starts spiking. So it starts becoming reasonably close to 1 only if your electric signal is larger than a certain threshold. Well, then the electron, this neuron will start emitting another signal that will be fed to the next layer. Okay, so this is again a very rough approximation of the brain, but it is what we use mathematically to model these networks of neurons. Now, so why do we trust these kind of functions? Well, there are, if you want, first of all, practical reasons, because I mean, it has been shown that numerically these functions are very well suited to approximate high-dimensional things, high-dimensional functions. But there are also, you know, if you are more on the mathematical side of things, there are also mathematical theorems that guarantee you that you can approximate essentially any well-behaved high-dimensional function. So these are all variations of actually a pre-machine learning theorem that was established by Kolmogorov and Arnold. I'm not going too much into the details of this, but essentially what this theorem tells you is that if you have a high-dimensional function, you can always write it as a composition, as a finite composition of a number of functions, which is only linear actually in the dimensionality of the input, which is, you know, non-trivial if you think about the problem. And this composition is just one-dimensional function, this capital phi and phi. Then this has been refined in general to the case of neural networks in the 80s, in the 90s, beginning of the 90s. This is what is called the universal approximation theorem, that it guarantees that you can write under the form of this deep net, actually shallow network is enough, any high-dimensional function, provided, this is the caveat, that you put a sufficiently large number of neurons, this n, and this number in the worst case can be exponential, but in practice we find in most applications that with an n which is not too large, you can typically describe very well even super complex functions. Okay. So this is the content of the mathematical theorems of the representability. The other ingredient that we need is the learning. And the learning, there is a spectrum of different techniques. Here I rank them more or less arbitrarily, or at least according to my taste, in terms of interest for applications in science. So we have supervised and supervised reinforcement learning. Unfortunately, the most complicated of these techniques are also what I think are more relevant for science. So, for example, unsupervised reinforcement are, I believe, among the most interesting for science, but they're also the more complicated to realize numerically. So let me give an example. So supervised learning is the easiest to understand. It's essentially the case where you want to approximate this high-dimensional function, knowing a bunch of values that this function takes on some data x. So in this case, x is for example, an image. So the set of inputs in this case is just the bits of this image in the digitalized form. And somebody has taken these pictures of numbers and has pre-classified them to say that this is a 5, this is a 0, this is a 4. Okay, so we know the value of this function that is supposed to classify these numbers on a bunch of x's. So essentially, supervised learning is regression. So it's a fit, if you want, of the weights that I have in my network, knowing the value of this function on a large number on a data set of pre-computed images. And this is what is done in the supervised case. And then you can use this function, for example, to classify a new image x, which has not been seen by the machine before. Okay? But this is essentially a fitting procedure. The more complex end of the spectrum is what is called reinforcement learning. And here, I mean, this is one of the earliest applications of reinforcement learning, but this is a case where you don't have an external data set of pre-solved solutions, but the machine, for example, in this case, plays against itself to try to beat, I mean, this game, so to do the score, the maximum score possible for this game. So this is a game that was very popular, at least for my generation in the 80s, 90s. So this, for example, was one of the first episodes where the machine starts playing against itself, tries to improve the score. You see that here it's not very good at doing that. But I mean, after some time, and during this reinforcement scheme, essentially the machine gets very good at playing these, and you can see that at the end it will also manage to find a trick. As you can see, this is the not quantum but classical tunneling trick that people in the 90s used to play to beat this game, and the machine actually also found this trick. Of course, this can be generalized, and it has been generalized to much more complicated cases like the game of Go, which is way more complicated than playing this game, and things really work nicely. Now, I mean, the applications to science and to physics have been numbers in all sorts of fields. So let me say that, so here you can find more or less a review of what has been done in the past couple of years, but historically, statistical physics has been the field that has the most connection with machine learning for historical reasons. And also particle physics has been one of the early adopters of techniques from machine learning, for example, to classify events at LHC and other things. But more recently, there's been a strong adoption of these methods that explains somehow the results that I showed you at the beginning on the archive. Also in astrophysics, chemistry for discovery of materials, and as I will show you today in quantum physics. So again, if you want to have a better overview, you can have a look at this review. Now, what about many-body quantum physics? So what can we do with machine learning? Essentially, what is the problem that we'd like to solve? Well, essentially, the problem is that if you have, for example, the simplest quantum system that you can think of, so let's say spin 1/2, then in this case, you know that the wave function is given by a superposition, linear superposition of the two basis states, up and down, with two coefficients, and these two coefficients essentially give you all the probabilities of observing up or down. So you have, you know, if you want a half dead or half alive Schrödinger's cat, and this is all fully encoded in these coefficients. So for the wave function is not too hard to analyze for one spin, 1 degree of freedom. But the problems start when you have a lot of spins, so when you have a lot of particles, a lot of electrons. And then in this case, the wave function is an exponential mess. So Walter Kohn, Nobel Prize in Chemistry, used to say that to some extent, the many-body wave function for a system of electrons is not even a legitimate scientific concept in his vision, because it contains so much information in theory that this could not even be potentially stored using all the atoms in the universe. So this was Walter Kahn's points of view. This is a bit extreme. I think that the wave function is still very reasonable if you want scientific concept, but the issue is that if you have many electrons, many spins, you have 2 to the n now coefficients, and describing exactly the properties of this system is a daunting task that you cannot do essentially with any technique, even with quantum computing. For example, if you want to prepare a very specific state, this is in general an exponentially complex task. And as a result of this exponential complexity, solving very important equations like Schrödinger's equation, which is an eigenvalue problem, as you know, for psi. I mean, if you look at the static problem, then this is also in general a task that you cannot solve exactly, even on a quantum computer. Let me stress that. You have to make some approximation. So that's where the quantum complexity lies in the many-body problem. Now, I mean, but if you look at that, I mean, as I was mentioning, even just in terms of storage, if you think about the wave function of 15 qubits, and you write down all the coefficients, you can maybe write all the coefficients if you fix some 32 or 64 bits accuracy on your coefficients using a book, let's say something like something as big as the Bible or something. You could still store all your coefficients in a book. And you see that with the increase of storing capabilities in classical hardware, nowadays we can store up to 54 qubits, the equivalent of the wave function of 54 qubits. But you see that essentially in 5,000 years, going from the ancient Egyptians to modern technology, we've only been able to advance our capabilities of storing wave functions by a factor of 5, which, if you think about the time that has passed, is not a lot. Again, the reason is that this growth is fully exponential, and at some point you won't be able, as also Walter Kahn was saying, to store the wave function using all the atoms in the universe if you stick to classical storage, at least. Okay, so it's clear that we have a storage problem for the wave function. However, the question that we have to ask as physicists and chemists, if you want, is whether this complexity is truly exponential or not. Meaning, is there some way around to this nominal complexity that we have written here? So do we really need all of summit to describe the wave function of 54 qubits, or can we do maybe using some smart trick better than that? Okay, so this is the main question that I would like to try to address today. And essentially it is based on the idea, on the perception that if we have a general wave function which lives in this huge Hilbert space of all possible states, so in general it is true that one arbitrary state, one psi, lies in this vector space if you're spins, or Hilbert space if you're continuous variables, it doesn't matter. But this is a huge space that you cannot even think of describing exactly on your computer. But it's also true that we are not interested in the most general, if you want, random state, but we are interested in the physical state. So we are interested in the green, if you want, much smaller subregion of this red intricate space, which represents only psi's that describe physical, for example, ground states of quantum Hamiltonians that emerge from physical interactions. Okay, so this is a huge simplification if you think about it, because we can attempt at not solving the most general, which is NP-hard, but we can try to solve some specific instances of problems that are in principle easier to solve. So the question is then, how can we access these corners? And I mean, there are two philosophies that I will highlight today. So the first approach is due to Feynman, and Feynman is not Feynman if you don't have some swear words, in this case, naturalism classical, damn it. I mean, Feynman pointed out that essentially you should build a quantum computer to simulate a quantum system. So this is, of course, a very well thought idea, and that's what people are doing these days. The idea is that at least you can go around this storage bottleneck if you use actual quantum bits to store the wave function. So it's clear that you solve the storage bottleneck if you use a wave function. that is implemented on quantum hardware. Even though, I mean, Feynman had in mind the analog simulation, but I mean, these days it has been rephrased in terms of digital computation. And the other approach, which, you know, I'm attributing to von Neumann a little bit artificially, but I'm sure that maybe von Neumann would agree. The other approach would be instead, let's try to tame, if you want, the wave function classically, so using classical machines, okay? And I like this quote by von Neumann because it says that if you tell me precisely what a machine cannot do, then I can always make a machine that will do just that, okay? So it was claiming that essentially if you can mathematically express your problem, then you can hopefully try to find a machine that can solve the problem for you. Of course, these are both extreme views to some extent, but somehow we have to find an agreement between the two views. So the first philosophy is essentially what you do on a quantum computer. And in this case, you have a quantum circuit, which is parameterized by a lot of variational parameters. For example, you have a unitary that is parameterized by some theta. For example, in the VQE scenario, what you do, the variational quantum eigensolver, what you do is that you're trying to find the ground state of a given Hamiltonian using the variational principle. And again, the philosophy is that you store the wave function instead of storing it in a hard disk, you store it on qubits. So you solve this storage problem. However, I mean, this is the key point. Even if you have a quantum computer, finding the ground state of a generic Hamiltonian is still, I mean, as far as we know, exponentially complex. Essentially, if I give you some generic Hamiltonian, just to give a random example, the Hadamard model, then there is no way you can find in polynomial time the ground state of the Hadamard model, even on a quantum computer. So it's because this amounts to preparing a very specific state and using only these knobs, this is in general exponentially complex. So it's clear that this quantum manifold problem really needs the interplay of both classical and quantum computing. We actually work on both. I like quantum computing a lot. It's not to discredit quantum computing, but today I will talk more actually about the classical side of things, so the machine learning part, if you want. And the idea on the machine learning part, which is to try to classically tame, if you want, the wave function, is to just look mathematically, you know, a la von Neumann at the wave function as the problem that you want to solve is essentially finding approximations of these high-dimensional functions. So what I want to do, and what we introduce in this paper, is the idea is that I can try, instead of storing the wave function, that is unfeasible, for a large number of particles, I try to find a blob, so a machine, you know, some brain that takes essentially an arbitrary string of quantum numbers, for example, for spins, and returns for this set of spins the value of the wave function amplitude. Okay, and in general, I mean, what we do is that, and what I call the neural network quantum states, is that we approximate, again, this high-dimensional function of these quantum numbers. I'm fixing a basis set. I express it as a deep network. So this is, again, a rewriting of what I told you about before, about these deep networks. So we have a first layer, which is a vector of quantum numbers that can be plus or minus 1, for example, for spins. And then you have a linear transformation, nonlinear, linear, nonlinear, linear. And the important point is that at the end, you have only one output, which is complex value that represents the amplitude of the wave function. Now, the applications that I will discuss in this talk are mostly in the context of simulating quantum systems. So these are in spirit closer to unsupervised and reinforcement learning, in the sense that we are not using any pre-solved solution. So we are not using any external data to simulate these quantum systems. And that's why I was saying at the beginning that in my opinion, it's crucial to have new applications of machine learning to science to try to always not use pre-computed solutions. Otherwise, there is also always the risk of inferring things that you already know. So, and in this case, you essentially will play a game against yourself to simulate quantum systems. So this can be connected also to the game that I was showing at the beginning. There is another part of the story which is about using quantum data. So, for example, experimental measurements. Unfortunately, I won't have the time to go through this, but if you're interested, we can talk about more later. So, simulation-driven. Well, this is all based on the variational principle. and it can be used for several applications. So starting from the problem of finding ground or excited states for a given Hamiltonian, or finding approximate solutions for the unitary dynamics, or even studying dissipative dynamics, so open quantum systems. So in this case, you would have, instead of having a wave function, you would have a neural network approximation of the density matrix. So today I will not discuss this part, but I will discuss applications from these two, and especially for ground state and the problem of approximating unitary dynamics on quantum computers. Now, so for the problem of ground state search, this is conceptually easier to understand because we just use the standard variational principle. So we have a Hamiltonian and we want to find the ground state by minimizing the expectation value of the Hamiltonian. And conceptually, and this was pointed out already by Macmillan in the 60s, you can rewrite this quantum expectation value as a statistical expectation value over a probability distribution, which is well positive, which is psi square. So essentially the Born probability distribution of an object, which is called in jargon the local energy, that depends only, and it can be computed efficiently, depends only on age. Okay? So the key insight is that you can write everything as a statistical expectation values, which is essentially what you do also in standard machine learning. And then you minimize this expectation value. I won't go into the details on how we do that, but I can guarantee you that also the energy gradient, so the gradient of the energy with respect to my variational parameters k, can be written itself as an expectation value over this Born distribution of some efficiently computable observable times the local energy. Okay, so this OK is in this case just the derivative of the wave function, of the log of the wave function. This is a technical point. Now, let me give you some applications. So the fruit fly for us, I mean, essentially the toy problem, no, not so toy, but the complicated, the easiest complicated problem we've been addressing in this, and also others have been addressing with neural networks, are frustrated spins. So this is a class of interacting spins in typically in 2 dimensions or even higher dimensions that cannot be solved exactly with any technique, even numerically. For example, quantum Monte Carlo has a severe sign problem in 2 dimensions. With tensor networks, you have entanglement and in some cases contraction problems in 2 dimensions. This problem is therefore really open for numerics. Is a very good benchmark for also new approaches. So the J1, J2 model is a model where you have interactions on nearest neighbors and then also interactions among the diagonal of the square lattice, Heisenberg-like interactions. And what we don't know is whether this model supports a spin liquid, so a disordered phase that is intervening between the 2 limits. So when J1 is large, you have the Heisenberg phase where you have an L order, so antiferromagnetic order. When J2 is large, you have a striped phase where instead you have columnar order. Is there something in the middle which is disordered? We don't know for sure. And the idea was to use somehow our neural network states to address this problem. This is work, let me mention that we've been doing, we've done in collaboration with Kenny Chu, who's from Singapore and who's been a strong collaborator on these projects. He's a student in Zurich in the group of Titus Neubert, but also very often collaborating with my group. And in this project, what we did is that we used a convolutional neural network, which is again a sequence of layers where the filters, so these weights, are taken to be short-ranged. So this is the key insight of this convolutional architecture that are the state-of-the-art for image recognition in 2 dimensions. And a nice property from the physical point of view is that the wave function, if you construct it as a convolutional state, is automatically, for example, translational invariant, so you can automatically satisfy some symmetries that you have in your system. Now, just to give you an idea of the progress that we've been doing from the first paper until today. So if you take the Heisenberg limit, which is already a non-trivial benchmark because we don't know the exact wave function even for the Heisenberg limit in 2 dimensions. This is the error that you make on the energy. Those were the first results with this naive RBM, if you want, that I used in the first paper, which was just 1 layer of a network with only 1 layer, so a very simple-minded network that nobody's using anymore in machine learning, but that I like for its simplicity. But in any case, with this architecture, increasing the width, alpha, so it's the width of the network, you could improve of what at the time were some results obtained, for example, with PEPs. This is the accuracy that you have on the ground state. If you use this mildly deep network, so we only have 4 or 5 layers, which is not a lot, you already get here in terms of accuracy on the energy. You know, if you actually use a deep network with some 15 or even 20 layers, so something that is much closer to what people do in actual machine learning applications, but still very far, at least 1 order of magnitude far. But even with that simple, relatively simple architecture, now we are around 4×10⁻⁵ accuracy. So, I mean, I think for all practical purposes, this is the most accurate result that you have on this system in 2 dimensions. Now, if you move now away from this point where we have also exact benchmarks that come from quantum Monte Carlo, because this is the point where you don't have the same problem, then, I mean, it turns out that we are competitive. We are not yet, you know, at the point where we can beat the world champions of Go, in this case of frustrated systems for all the values of J2, which is the thing that somehow controls the amount of frustration. And you can see from this diagram, this is the energy that we have compared to the other energies. So these are all variational techniques. So if the points lie in this part of the diagram, it means that our NQS, network condensate energy, are typically more accurate. If these points are here, it means that our energies are worse. So in this, again, this was the first work, and there's more going on where we improve these results. But in this first work, we observed that we can improve on these other results, for example, of dealing with the MRG or other fermionic approaches, apart from a region in the middle of the spectrum, essentially, which is unfortunately close to the transition. But again, also improving on these points is a highly non-trivial task, considering that this model has been studied for more than 20 years. So what is the issue with these points? So you can ask yourself why you don't have that performance that you would like in that part of the phase diagram. Well, the origin of the challenge is, there are actually 2 challenges. So the first one is enforcing the right symmetries in the wave function. So in the wave function that we use here, this convolutional state, we didn't have a handle to, for example, enforce SU2 symmetry, which is very important in this problem. And we know that our solutions break SU2 symmetry quite strongly, for example, in this point. So this is one of the reasons why we are not so accurate. The other reason is that there is, if you want, a deeper issue, which is related to the problem of how many samples you need to learn a certain phase of matter, if you want to learn a certain wave function. This has been discussed in this paper with some numerical experiments on some frustrated models. So, for example, what they show in this plot is the overlap. So essentially, if I give you in this case, the exact solution, and you try to learn it with your wave function, neural network state, they clearly see that if you have large frustration, so in this case, large frustration corresponded to large J2, this was a slightly different model. They saw that essentially the number of samples, so this axis is proportional to the number of samples that you need to see to learn the wave function to some accuracy. So accuracy, perfect accuracy is 1 in these units. You see that the number of samples increases with J2. So something which is very remarkable is that there is a sort of phase transition in the accuracy. So you need the minimum amount of samples to learn with good accuracy a certain phase of matter. And this reflects, maybe not too surprisingly, the fact that if you are in a highly frustrated phase, you also need to see a lot of different configurations to understand actually what is the nature of the phase. So this is true also for classical fields. There is nothing too specific of the quantum case. And essentially what we are limited by is we are limited because of the fact that we cannot see a lot of an infinite number of samples. However, in our simulations, what seems promising, at least if you have an optimistic view on this, and I think there's reasons to have that, the critical number of samples, essentially where this phase transition happens, does not depend too strongly on system size. So if you look at the number of spins that you have here from 20 to 36, the number of critical samples, the critical number of samples does not scale, too abruptly. I mean, at least for what they could do in this case. Again, these are small systems, so it's hard to infer large conclusions. But this seems to confirm the hypothesis that we had at the beginning, that if you want to describe a physical ground state, you typically don't need to see, exponentially many things, but only a number of features, in this case, number of samples that is not scaling too wildly with system size.
Excuse me, Giuseppe, can I ask a quick question on this?
Sure.
So this last paper you mentioned by Bagrov and others, this is a supervised learning. So they know a wave function and they try to train a neural network and see whether the neural network can represent effectively this wave function. Is that right?
Yeah, that's correct.
Okay, but what you were talking before is unsupervised, where you're trying to optimize, lower the energy. So is it obvious that if you cannot represent well the wave function with supervised learning, then it's as bad also for unsupervised learning?
It's not obvious, but they show numerical evidence for that. I would say that this is an easier problem. As I was mentioning, this is, as you were mentioning too, this is supervised. So if for this is a problem, you already see this transition, I think that you expect to see the same feature also for the harder problem, which is this unsupervised or variational learning. This is an argument. I don't have a theorem, and I think that nobody has it at the moment, unfortunately.
Yeah. Okay, thanks.
No problem. Okay, now, I mean, the other thing that I wanted to briefly mention, I mean, in the last few minutes that I have left, is about, if you want, so now we were concerned about simulating ground state properties. Now I want to simulate, if you want, dynamical properties. And the simplest way of looking at dynamical properties is through quantum circuits. Okay, so a quantum circuit essentially can be thought of as a sequence of gates, so local unitaries that come from a set of universal gates. So in this case, what I will consider is a set of universal gates that is done by these three gates. So, for example, just single qubit rotation with some arbitrary angle phi h, which now is not the Hamiltonian anymore, but it's the Hadamard gate. So superpositions or rotations in the x direction. And this is the 2-qubit controlled Z rotations. So this is the entanglement gate, if you want, that performs controlled Z rotations. Okay. So I will consider all circuits that can be done, and essentially all circuits can be written in terms of these three gates. So essentially what we did in this paper, in collaboration also with Bella Bauer and Microsoft, and with my students Johnson, was to show that if you have, for example, a very simple, again, simple-minded RBM, one-layer neural network, and you think of this as a wave function, and you try to apply one of these gates, well, it turns out that for most of these gates, you can the output state is still of the RBM form, it's still a neural network state, but with some modified weights. So, for example, if you apply a local rotation in this direction, you have a state with modified weights that connect to this pin. So if you're applying your gate on this qubit, sorry, you will modify these weights. This can be derived analytically. If you apply control Z rotation, you can derive that, you can show that all you need to do is to add another neuron, if you want, in your network that connects these two things, and you also know analytically how to determine these weights. So all the actions of these two, even of this entangling gate that can be arbitrarily far apart, notice that, those can be done exactly. The only issue, I mean, otherwise we would have solved everything, is that when you apply the Hadamard, you get on a neural network state, you don't get out a simple neural network. So you don't get out just a simple neural network quantum state, but you get a superposition of two neural network quantum states, which in general is not equivalent to a new neural network with different weights. So this was already shown in this paper by Gao and Duan. However, what we do in our paper is that we use a variational principle to approximate this output state as much as possible with another neural network. So for example, if you think of this output state as something that is obtained by applying the Hadamard on my initial state, which is described by some weights, and it is a neural network, then I try to find a new neural network with other weights, W prime, that approximates this phi as much as possible. So I know that in general, I cannot do that exactly, but I want to do this numerically. Okay, so this is my now, if you want, time-independent variational principle. And the goal is to minimize the infidelity. I mean, this is not exactly the infidelity, but this is the log of the minus the log of the fidelity. This is the loss function that we use. So this is the thing that we minimize as a function of these weights W prime. Okay. We can do this also with a technique which is based on sampling. And these were the early results that we obtained. For example, if you consider the initial state, which is the ground state of a 1D or 2D transverse field Ising model at the critical point, so these are typically highly entangled states. And then you do the Hadamard transform, so you just apply Hadamard on each qubit. So this is already something that it's pretty hard to do. You see that these are the intermediate fidelities of this approximation step that we do. You typically you get pretty good intermediate results with relatively small networks, and you can do this also for two-dimensional systems up to, in this case, 64 qubits, but we can do more. And this is the final fidelity that you get in 1D, where you have also the exact solution, and you see that the final fidelities are pretty high. Now, the interest of this exercise, if you want, is to compare also this and to benchmark quantum computers versus what you can do with classical simulations, in the sense that in the classical simulation, I have a wave function. So I'm not approximating a variational wave function. So I'm not storing, if you want, or having an approximation of the state, which is exact. I have some variational error. And our point in this paper, that was also made by other papers following us, is that if you have some variational error, you can somehow compare this variational error to the noise level that you have on the quantum computer, in the sense that if you run your quantum algorithm on your quantum computer, you also, the final state that you will get out of this Hadamard transform, for example, will not be exact, simply because each of these gates has some noise. The hardware has noise. So if you don't error correct that, you will have noise. For example, if you plot the fidelity versus the noise level for the quantum computer in these experiments, you will see that it goes like this. So typically it goes exponentially with the noise level. And the noise level that we have with the RBM, so this very simple network, corresponds to an error on the fidelity that is in the 10 to the minus 3, if you want, single gate noise level, which is pretty good for modern standards. And it's again, recalling that this is a very simple network, I think that we will have, I mean, essentially you can think that we have a classical but noisy quantum computer that can perform some interesting quantum algorithms. So apart from that, another thing that we did more recently is simulating quantum optimization algorithms. So this is the so-called QAOA technique, which is introduced by Fari and others in this paper, which has also been implemented by Google in a recent paper in their hardware. So I won't go too much into the details of this, but the idea is that you want to solve some classical optimization problem, which is typically encoded by some Ising Hamiltonian with some weights Wij that encode your optimization problem. And you want to find the ground state of this classical Hamiltonian using essentially a quantum circuit. And there are reasons to believe that quantum computing can be more effective of solving that, maybe because you can use quantum effects essentially to move from one minimum to the other. What we showed is that we can also approximate the circuit, this kind of circuits with our simple-minded RBMs. So this is the case where the problem at hand was a three-regular random graph. So you want to find the ground state of this three-regular random graph Ising model. It's just an example that was also implemented on quantum hardware. You see that this is the cost function that you get as a function of these gate parameters. And you can see that what we can compute with the RBM is typically comparable to what you can do in the exact case. These are small systems, but if you go on move on larger systems where you don't have the exact results anymore, apart from when you consider only one layer, that can be done also analytically. But if you have more than one layer of qubits, of gates, so for example, if you go on 54 qubits, which is more or less state of the art for quantum hardware, up to p equal 4. So depth 4, which corresponds to 20 clock cycles. I think it's almost 1,000 gates in total, and now I don't remember the exact numbers. You can find them in the paper. So this is something which is already pretty challenging for modern hardware. You can't really access this p equal 4 with good fidelities. But p equal 4, essentially, we have some curve for this cost function, the function of gamma, and essentially we believe that this is the most accurate thing that we can compute classically at this point with this with classical methods. And it will be interesting also to compare this with actual experiments once they will become available at this level of depth, and they can simulate also in the quantum case this kind of circuits. They can run these quantum circuits, not simulate. Just to give you an idea, I mean, if you try to use other techniques, so for example, matrix polar states, which are by themselves suitable and very powerful to describe one-dimensional problems. So if you try to apply them to describe this kind of circuits, which are not intrinsically one-dimensional, so this is not, the target applications for matrix polar states. So essentially, you would find that, for example, if you want to simulate these circuits with the same accuracy that you have with these RBMs that are long range, you will need a bond dimension which is of the order of 10 to the 5 or something, which corresponds to about 10 to the 10 parameters. So this is something that is very challenging to do if you have tensor network representation, for example, based on MPS. So this shows you that, again, if you have a neural network and you can encode more entanglement, typically this can be helpful also to simulate longer time circuits. Okay, so I want to actually skip this slide, and this was a discussion on the entanglement properties of quantum states. I will just flash the result, and the result is that if you have a quantum state described by a convnet, for example, you can show that you can encode volume law states, so highly entangled state, efficiently, so meaning that you need a number of parameters that scales only polynomially in the system size. And this is more efficient than taking just a shallow network, for example, where you have long-range interactions. Okay, the final word is about the software. I mean, I couldn't help myself. I have to advertise our software. It's Netket. It's a software where we completely open source, so you can collaborate or you can have a look at it, use it for free, of course, that we are now developing at EPFL. And it is in Python and allows you to simulate classically these circuit, these ground state properties mostly, but it will soon support also more dynamical properties. And again, this is purely in Python. If you are interested, you should definitely have a look at it. Okay, so this is my outlook. So I think that I've shown you several applications of these neural network quantum states. There are some challenges, as I was highlighting. There is this issue of the physical symmetries, the number of samples that also we don't know how it determines the accuracy of our variational calculations. And I think that in general, the deep question, which is still to be answered, is how to characterize essentially this corner of the complexity of accessing these corners of Hilbert space with any classical technique, essentially. And in this sense, I think that we need better and more meaningful, to some extent, the measure of classical simulation complexity than, for example, entanglement entropy. Entanglement entropy is a very nice measure of complexity, but it is relevant only for a very specific class of wave functions, which are tensor networks. But as soon as you move to other classes of wave functions, this is not related directly to the complexity of simulating classically that kind of states. We know a lot of examples of highly entangled states that can be simulated efficiently classically. So there must be some other, who knows what, measure of complexity out there that we should try to find as a community, maybe. And this is always my cry for help, and to address to the new generations, maybe, to find and rethink this problem from ground up. And thank you for your attention, and I would be happy to take some questions.
Okay, thank you very much, Giuseppe, for this very, very nice talk and overview of everything, and also some nice detail on your recent researches. So the talk is open for questions. If you have any questions, you can either directly ask here, or you can type it in the chat and I will ask the question for you. And maybe to give you time to think about the question or the chat, maybe I can ask the first question. So you have been thinking about symmetries in the neural networks so that it can help you to find these ground states, for example. Yeah. Now, do you think that this can bring us to a new class of neural networks which could actually be useful outside of physics?
Yes, that's an excellent question, and I think that the answer is definitely yes. So there is some work that has been that people in especially in the high energy community are doing, where they try to find gauge invariant neural networks or even you know, SU2 invariant neural networks, something like that. So these works actually are pretty interesting because then they can be recycled if you want, not only from physics application, but also for, I don't know, image classification problems of three-dimensional objects that intrinsically have some symmetry. And indeed, the interplay of these two communities, you know, physics and machine learning, is already producing some interesting results. Other interesting results that come out of this interplay concern, for example, the understanding of the learning somehow dynamics. So there is a lot of now studies in the statistical physics, but it's clear that it's believed that, for example, gradient descent performs a global optimization. When you have noise, performs a sort of global optimization instead of just local optimization, and this also serves as a regularizer for your solutions. And there are a lot of arguments in statistical physics to somehow justify this kind of understanding of why SGD essentially works so well.
Okay, thank you very much. So maybe now we will have a question from the audience.
Yeah, maybe I have like two nice questions. Hi, Giuseppe, this is Aurelia from the IPC in Spain. Thank you very much for the very instructive and clear presentation. I really, really enjoyed it. And I'm very new to the field, so my two questions are: first, is it possible to train a data set on a smaller kind of chain, like, and then find a solution for higher, for systems of higher dimensions? And the second question is, at some point when you started talking about dynamics, you said, or at least I understood, it was nice, it was better to think about solving dynamics through circuits. So for this, I would assume something like trotterization or something. So what are your views, like, to, if you can tell a bit more about like dynamics and what the project for Netket or something in that direction?
Yes, okay, so coming to you, so your first question is if I can recycle essentially the solutions that I have on small systems to study larger systems, if I understand correctly. So the answer is yes, to some extent, because if you use, actually, I think it's a work that has been done by Dario also and others, if I remember correctly, right, Dario? Yeah.
But yes, we did something on that. Thank you.
Yeah. Yeah. So, but I mean, the main idea, for example, if you take a COMNet with short-range filters, you can just, if you want to take the same filters that you've trained on the small system and you use the same filters on the larger system, this will give a good starting point. This doesn't mean that the final solution will be exact, but you can. This is a good starting point for your variational procedure, which in some cases, if you have short-range phases, typically works very well, actually, without retraining. Now, the other issue you asked is for the dynamics. So I discussed only trotterizations, if you want, because I just wanted to tell you about the latest work we've been doing. But there is another line of research, which is based on time-dependent variational Monte Carlo, which allows you to essentially solve the time-dependent Schrödinger's equation approximately with a variational principle. So in that case, you don't need to trotterize, and you just use the same essentially tools that you have for the ground state. So you use this Fisher information. I mean, this quantum geometric tensor. I mean, so we are going to implement. Actually, these things are already implemented, but not yet in the public branch of Netket. They will be released hopefully soon once we stabilize things. And we will release, I think, first the other thing actually. So the thing where you solve the unauthorized dynamics directly for the Hamiltonian. If that's what your question. That was your question.
Yeah, it's perfect. Thank you very much.
Thank you, Riley, for the question. Anybody else?
Hello. Hello. Can I ask one quick question?
Please go ahead.
Yeah. First of all, thanks so much for the talk. I really enjoyed. So my question is that do you have an intuition for what is the limitation of this machine learning for quantum many-body system? In your opinion, what is the limitation of
Yes, so I think that one limitation that I was discussing is this one. Sorry. Okay, so essentially is what is called the sampling complexity in the jargon. So essentially, how many samples do I need to describe a given quantum state? So if I have, for example, a random quantum state, so a state which is in this boldly, squarely in this red region of the Hilbert space that I was showing at the beginning, not in the green one, then there is no way you can compress down that state with any reasonable wave function. Essentially, because that is a random state, and it's because of the Shannon theorems, essentially you cannot compress that. There's no way you can compress it. So it would mean that you would need still an exponentially large number of parameters. But my point was that typically physical states are not random. They might need a lot of parameters because, for example, if you have a disordered phase, you might need a lot of parameters, but this is still not entirely random in the sense of random state in Hilbert space. It's still the ground state of a physical Hamiltonian. Okay? So the limitation is essentially the number of samples and the existence of a structure. Okay. So also, if you try to simulate the random circuit that Google is doing with these machines, this wouldn't work because these circuits are essentially random. There is nothing structured, and they are also for this reason not very useful for physics applications.
Thanks so much for the answer.
Thank you.
Any other questions? Maybe ask another one. So I've actually played a little bit with your Netket, of course, and some people in my group. But let's say we take one of the students today, listen to your talk and is very excited about it and would like to play with Netket and wants to solve some problems. Okay. Now there are various neural networks architectures that they can start to play with. So what are your recommendations? How do you think about, okay, for this problem, I will use this one, or for this other problem, I will use this other one. And there are also many hyperparameters. So how to explore in an efficient way?
So you mean like to find the ground state of some Hamiltonian?
Yes, no, let's say, for example, should I start straight away with an RBM, maybe it's okay, or should I really go straight away for a convolutional neural network? And how do I think about how many layers should I keep and all the various other hyperparameters? Because there's quite a few.
No, I understand. So, okay, so my point, my personal taste is to start first with simple things. So that's why, I started with the RBMs. And then once you're more familiar with that, you can try to move on. So once you understand the limits of a simple network where you can control everything, essentially, then you move forward. But the other approach is that, and that's why we need to do that also as a community, is to have an atlas of pre-solved problems. No? So, for example, I can have a database of pre-solved wave functions that solve approximately some ground state of some Hamiltonians. So you have this kind of network structure that are convolutional states that work typically for this problem. In our experience, typically one architecture that works for one problem also works for another problem. This is the main. I mean, if you are talking about spins, then, I mean, there is the issues of symmetries for fermions. That's another story I didn't even talk about. But if you talk about spins, if you have some convenates, some structure typically works just fine for many different problems. So yeah, what is missing, what I would suggest is to start from some architecture that has already worked for a relatively similar problem, and then you start modifying it accordingly if you are not satisfied. I mean, unfortunately, this is the big problem, if you want, of what the old machine learning. It is to some extent still empirical, in the sense that finding the optimal structure is not possible a priori. You have to fight with it.
Yes, yes. And also other things are maybe not so clear. For example, a wave function, you could represent it with two neural networks, one for the phases, one for the probabilities, or using complex numbers. That it seems still needs to be investigated. Is that correct?
So this is a completely open problem. I think that somebody should really seriously tackle this problem really systematically, because we don't have a clear-cut answer to that. So is it better to use complex weights? Is it better to use real weights, but two outputs, as you say, two separate networks that don't talk to each other, one for the, there's several possibilities. Honestly, my feeling is that complex weights are still more powerful, but they are much harder to train than real weights, especially because you have singularities in the activation functions that you don't have in the real case, right? So you have poles in the complex plane. So this is the reason why I think that much more, I mean, this is maybe my fault because I started with complex weights and people also liked complex weights thereafter. But I think that we should investigate more. And I mean, in more recent works, we are also using actually real weights, the case where we have two outputs. And we try to see what's the best strategy also to parameterize the phase. There's a lot of very interesting works from Oxford, where they try to see actually how to parameterize the phase in a way that makes sense, that you don't get stuck in local minima of the energy. This is also a very important problem. And again, please study this because it's very important and poorly understood. But this is mostly a matter of having some theoretical argument coupled to some easy simulations.
Thank you very much. One last call for questions from the audience. Okay. Seems like people are quite happy with your talk. Thank you very much, Giuseppe. It was a pleasure. We hope to see you soon physically.
Thank you. Yeah. I really hope so. And I wish you well and stay safe.
Yes. Thank you very much.
Bye-bye.
Bye-bye.